Namaste. In this session, I will teach you GC essentials or gas chromatography essential for every pharma professionals. In this session, you will learn what is gas chromatography, what are the different types of gas chromatography, GC components and their function in GC, how to read GC chromatogram, GC chromatography terms like RT, RRT, theoretical plate and tailing factor, types of GC columns, what is the difference between GC and HPLC, GC column selection procedure, GC column chemistry, GC column bleeding, what is the split ratio in GC, separation mechanism, modes of calculation, GC detectors, how to operate GC, GC applications, advantages and disadvantages of GC, how to design GC method, GC method development steps, case studies, top interview questions asked on GC. Gas chromatography or GC. Gas chromatography is a chromatography technique used to separate volatile components. The components to be separated are distributed between two phases, one of which is the stationary phase and second is the mobile phase, which is gas. The mobile phase is called carrier gas, and in GC generally helium, nitrogen and hydrogen is used as a carrier gas. Separation occurs as a result of adsorption desorption action during the movement of sample components along the stationary phase, and the separation is due to differences in the distribution coefficient of the sample components. I am going to discuss adsorption desorption taking help of flow diagram. See, when we inject the sample mixture, let us say sample mixture contains methanol, ethanol and acetone. When it enters into the column, each methanol, ethanol and acetone will interact with different capacity with the stationary phase, since each having different polarity, and finally they get separated and we get chromatogram containing peak of methanol, ethanol and acetone in GC. Types of gas chromatography. There are two types of gas chromatography. One is gas solid chromatography. Second is gas liquid chromatography. Nowadays, gas solid chromatography is not used in the industries, since it doesn't give reproducible result, and secondly, column efficiency is very low in gas solid chromatography. GC components and their functions. The following are the main GC components in GC: carrier gas, makeup gas, flow control valve, injector, liner, GC column, column oven, detector, data processor, zero air, hydrogen. I am going to discuss each component in details with the help of GC system flow diagram in the next. GC system flow diagram. This is the carrier gas cylinder containing the carrier gas. This is the flow control valve to adjust the flow of the carrier gas. This is the injector to inject the sample. This is column oven which maintains temperature of the GC column at high temperature or as per method requirement. This is GC column which is responsible to separate each component from the sample mixture. This is detector which detect each component and convert them into the signal and send that signal into the data processor, and data processor converts signal into the chromatographic peak, and we get peak of the each component in the GC chromatogram. Let us consider sample mixture contains methanol, ethanol, propanol, acetone and toluene. Now, what will happen if we are injecting the sample in the GC? Sample will enter into the GC column. Since each methanol, ethanol, propanol, acetone and toluene has the different polarity, therefore each component will interact with different capacity with the stationary phase. Among these molecules, methanol, ethanol and propanol will interact less with the stationary phase and they will elute first from the column. Acetone and toluene are more nonpolar. They will interact more with the stationary phase and they will retain in the column and elute in the last from the column. And hence, due to difference in interaction of each component with the stationary phase due to difference in polarity, each methanol and ethanol are getting separated in GC. Now, how we get the peak? First, methanol will come out from the GC and will go in the detector. Detector detects it and convert it into the signal and send that signal to the data processor, and data processor convert it into peak of methanol. Then after, ethanol will come out from the column and will go in detector. Detector detects it and send the signal to the data processor convert it the peak of ethanol. Then after, propanol elutes and goes in the detector. Detector detects it and convert it into the signal of propanol and send that signal to data processor, and data processor converts peak of propanol. Then after, acetone come out from the GC column and goes in the detector. Detector detects it and send that signal to the data processor, and data processor convert it to the peak of acetone. Then after, toluene comes out from the column and goes in detector. Detector detects it and convert it into the signal of toluene and send that signal to the data processor, and data processor convert it into the peak of toluene in the chromatogram. In this way, we get peak of each methanol, ethanol, propanol, acetone and toluene in the GC chromatogram. This is the basic separation mechanism of different components in the GC. How to read GC chromatogram? Now question comes, what is GC chromatogram? GC chromatogram is a two-dimensional plot of retention time, that is the time in minute or second, and area response. Retention time is in x-axis, area response is in y-axis. Now question comes, what is the retention time? I am going to discuss in this slide in details. This is the peak height or height of the peak. Components of a chromatogram. Retention time, the time at which a peak is eluting is called retention time of that peak. Suppose this peak is eluting at 10 minutes, then 10 minutes will be retention time of this peak. Similarly, if this peak is eluting at 17 minutes, then RT of this peak will be 17 minutes. Peak area. Area under the peak like this is called peak area. Peak height. The height between peak maxima and baseline of the peak is called peak height, and it is measured in this way. Baseline I have already discussed in the previous slide, and it is the response of the carrier gas, like this is the baseline. Peak integration, the process of calculating area of a peak is called peak integration. It is calculated by simple mathematical formula, that is half into height into width of the peak. Broadening or peak broadening. See, these peaks are sharp, but if your column is not good, then shape of the peak may change and they may take more time to elute. Means peak size is deviating from its original size. It taking a lot of time in elution. This phenomena is called peak broadening. Now question come, what are the different chromatography terms used in GC? Peak, retention time, relative retention time, theoretical plate, HETP, resolution or R, tailing factor. Out of these, I have already discussed about peak and retention time. Coming to RRT. Suppose chromatogram containing two peaks, one is eluting at 10 minutes and another peak is eluting at 5 minutes. The peak which is eluting at 5 minutes is the main peak, and the peak which is eluting at 10 minutes is the impurity peak. then RRT will be 10 divided by 5, that is 2, 4 peak 2 or impurity peak. Hence, we can define that RRT is the relative location of an impurity peak with respect to main analyte peak in the chromatogram. Rest of the term I am going to discuss in upcoming slide. I will also discuss calculation mode. Now coming to resolution in. What is resolution in GC? Resolution is one of the widely used system suitability parameter and it is denoted by R. It tells about the separation between two adjacent peaks in the chromatogram. Adjacent word is very important. Now I am going to explain the same. See chromatogram 1. Peak 1 and peak 2 are adjacent peak. Peak 2 and peak 3 is the adjacent peak. Peak 3 and peak 4 is adjacent peak. Peak 4 and peak 5 is the adjacent peak. Peak 1 and peak 3 is not adjacent peak. Peak 3 and peak 5 is not adjacent peak. In interview also question is asked, can we check resolution between peak 1 and peak 3? Your answer will be no. In chromatogram 1, each peak is well separated with adjacent peak, but in chromatogram peaks are not separated with its adjacent peak. Hence, chromatogram 2 is not acceptable, but chromatogram 1 will be acceptable. Now, question comes, how R will be calculated? I am going to discuss in next slide. In industry, two formula are used to calculate R. First is R is equal to 2 into T2 minus T1 divided by W1 plus W2, where T2 is the retention time of the second peak, T1 is the retention time of the first peak, W1 is the width of the first peak, W2 is the width of the second peak. In formula 2, R is equal to 1 upon 4 root under n k divided by 1 plus k, where n is the column efficiency, k is capacity factor. Out of these two formulas, formula 1 is widely used in the industry to calculate resolution. Now question comes, which parameter affect resolution? I am going to discuss in next slide. Any parameter which can increase retention time can increase the resolution. Any parameter which can decrease width of the peak can increase the resolution. Any parameter which can increase the capacity factor which can increase the resolution. Formula 2 is widely used in method development. Now column efficiency. On increasing column efficiency, resolution is increased. Temperature resolution may increase or decrease depending upon its effect on retention time and width. Retention time, on increasing retention time, resolution is increased. Width of the peak, if width is decreased, resolution will increase. Peak tailing, on decreasing peak tailing, resolution is increased. Injection volume, on decreasing injection volume, resolution is increased. Column length, on increasing column length, resolution is increased. Peak shape, when peak is a sharp, resolution will be better. Film thickness of the stationary phase, higher the film thickness, lesser is the resolution. Now coming to theoretical plate. Now I am going to discuss what theoretical plate or column efficiency. Theoretical plate or column efficiency is denoted by N, and it is the second widely used chromatography term in the system suitability test. It tells about sharpness or narrowness of the peak. See, peak 1 is sharp than peak 2. Peak 2 is more sharp than peak 3. Peak 3 is more sharp than peak 4. Peak 4 is more sharp than peak 5. It means when we are going from left to right, sharpness is increased. Then what will happen? Means if sharpness will decrease, column efficiency will decrease, and hence column will not able to separate more components. If theoretical plate or column efficiency is more like 10,000, 50,000, it means this column can separate multiple components in a single run. Suppose N is less about 1000, that column will have broad peak and that column will not separate several components in a single run. See, these peaks are broad, hence keep in mind column having high theoretical plate when you are going to develop any GC method. Now question comes, how N will be calculated? I am going to discuss. Two formulas are used to calculate theoretical plate in industries. N is equal to 16 retention time divided by width whole square. Second formula is N is equal to 5.45 retention time divided by width at half height whole square. This formula is also used, but it is rarely used in the industries. I am not going to discuss the same. Out of two, formula 1 means N is equal to 16, T divided by W whole square is widely used in the industry. Now question comes, what factor affect the theoretical plate? Any factor which increase the retention. Tailing factor. Now I am going to discuss in details. See, peak 2. Peak 2 is symmetrical or in well shaped, and hence this peak is called symmetrical peak or ideal peak, and it is acceptable in GC or HPLC. Coming to peak 1, in peak 1 there is deformation at the front of the peak, and this phenomena is called peak fronting or peak containing fronting. Coming to peak 3, there is a deformation of the peak at the tail of the peak. Such phenomena is called peak tailing. Now question comes, how it is calculated? I am going to discuss. Tailing is calculated by this formula. T is equal to x plus y divided by 2x, where x is equal to distance between front part of the peak to peak maxima, y is equal to distance between peak maxima and peak tail. When T is equal to 1, peak is ideal like symmetrical peak and it is acceptable. When T is equal to more than 1, it means there is tailing in the peak. When T is equal to less than 1, it means there is fronting in the peak. Now, I am going to discuss types of GC columns. Two types of GC columns are widely used in the industries. First is the packed column, second is the capillary column. The packed column is a tube packed with the support material coated with liquid stationary phase. The most widely used and readily available support material is diatomaceous earth or siliceous material. The column is made of glass or stainless steel. Its length is 2 to 6 meter and its diameter is 1 upon 4 inch to 1 upon 8 inch. The efficiency of column is low, that is 1000 to 2000, and that is the reason packed column is not used in the industries. This is the picture of the packed column and this is the chromatogram of the packed column which we are getting during the analysis. Each peak is broad, that is the reason packed column doesn't give reproducible result. Capillary columns. These columns are made of fused silica and their inner wall is coated with liquid stationary phase. These columns are hollow from the inside. The length of the capillary column is 10 meter to 150 meter and its internal diameter is 0.1 mm to 0.7 mm. See, this is the picture of the capillary column. Its length is 10 meter to 150 meter. This is the outer side of the capillary column which is made of fused silica. This is the inner side which is coated with immobilized stationary phase which is responsible for the separation of the component in the sample mixture. This is the diameter of the capillary column which is 0.1 to 0.7 mm. This is the length of the column which is 10 meter to 150 meter. The columns have extremely high column efficiency or theoretical plate, that is 1 lakh to 1,50,000. See, we get very sharp peak in capillary column and that is the reason capillary column always gives reproducible result. What is the difference between GC and HPLC? I am going to discuss. In GC, non-volatile molecules cannot be analyzed like esters. Acetate means only volatile compound can be analyzed in GC. In HPLC, non-volatile molecules can easily be analyzed. In GC, mobile phase is a gas. Generally, nitrogen and helium are used as a carrier gas, whereas in HPLC, a mobile phase is liquid. In GC, stationary phase is immobilized liquid, whereas in HPLC, stationary phase is a solid. In GC, capillary column is used, whereas in HPLC, packed columns are used. In GC, one can get higher theoretical plate or column efficiency. For example, one can get up to 10,000 to 1,50,000, whereas in HPLC, one can get theoretical plate 10,000 to 50,000. GC, we are getting lower tailing in peak compared to HPLC. In GC, one can get sharp peak compared to HPLC. In GC, generally, flame ionization detector is widely used in most of the analysis, whereas in HPLC, UV detector is widely used for most of the analysis. In GC, internal standard is used for quantitative analysis, whereas in HPLC, internal standard is not used. In GC, analysis is performed at higher temperature, whereas in HPLC, analysis is performed at a lower temperature. The maximum temperature can be used in HPLC is less than or equal to 80 degree C. Thermally degradable molecules cannot be analyzed on GC, whereas same can be analyzed on HPLC. In GC, analysis time is less compared to HPLC. In GC, analysis cost is less than HPLC. GC column length is 10 meter to 150 meter. In HPLC, column length is 5 centimeter to 30 centimeter. In GC, we are getting very sharp peak like this, whereas in HPLC, we get broad peak like this. GC column selection. GC column selection is based on like dissolves like, or like interacts like, or like attracts like. Non-polar columns for non-polar solids means if you have to separate non-polar molecules, you should use non-polar column. Strongly polar columns for strongly polar compounds. Suppose you have to analyze strongly polar molecules, then you should choose strongly polar GC column. Suppose you have to analyze intermediate polar molecules or compounds containing different polarity. In that case, you should use mid-polar column. I am going to discuss in details in next slide. GC column chemistry. There are three types of stationary phase. One is non-polar stationary phase, second is a polar stationary phase, third is intermediate polar stationary phase. Now question comes, what is the non-polar stationary phase? See in this picture, suppose you are replacing phenyl ring with CH3, then column stationary phase will be dimethyl polysiloxane and it will be non-polar, and dimethyl polysiloxane is used for separation of non-polar compound. Suppose it is phenyl row ring in the structure, then column is phenyl or diphenyl dimethyl polysiloxane. This is polar than dimethyl polysiloxane. If you are replacing one of the phenyl group with propyl cyano group, then this column will be more polar than this column. If you are replacing two phenyl group with the propyl cyano group or cyanopropyl group, then this column, resulting column will be more polar than this column, and based on polarity we are selecting the column in the method development. I am going to discuss in details in upcoming Generally, we see in the method written DB1 column, DB5 column, DB6 to 4 column, what they are. Suppose DB5 or DB1, it contains 5% phenyl and 95% dimethyl polysiloxane. It is the non-polar and it is used for separation of non-polar molecules. DB1, it contains 100% dimethyl polysiloxane. It is also used for separation of non-polar molecules. DB6 to 4, it contains 6% cyanopropyl phenyl and 94% dimethyl polysiloxane, and it is used for separation of molecules having different polarity. Similarly, DB1701U contains 14% cyanopropyl phenyl and 86% methyl polysiloxane. It is mid-polar column. Similarly, DB23, it contains 23% cyanopropyl methyl and 77% methyl polysiloxane. It is a polar column and it is used for separation of polar molecules. Wax or polyethylene glycol column is a polar column and it is used for separation of polar. GC column bleeding. Generally in GC we see a smooth baseline with sharp peak, but when you are not using proper GC operating parameter, then a lot of noise is coming and you are getting such type of peak. This phenomena is called GC column bleeding. Now question come, why it happens? The main reason is if you are using detector temperature or injector temperature more than recommended by the manufacturer, in that case a stationary phase come out from the column and goes in the detector, and that is the reason you get such type of disturbed baseline in the GC chromatogram. Now question, what is its impact? You get low signal to noise ratio. If your column is good, you are using proper system condition as recommended, then you will get high signal to noise ratio for sensitivity solution or QL solution. Now question come, what is the function of makeup gas in GC? Makeup gas maintain detector sensitivity, it adjusts flow rate, it increases signal to noise ratio. What is the split ratio in GC? In method, generally you see written like 10:1, 20:1. What is this? It means, suppose coming to this 10:1, it indicates that 10 part of the sample goes in the waste and 1 part of the sample goes in the column. Here 20 part goes in the waste, 1 part goes in the column. Now question come, what is its benefit? It reduces the column overload and you get sharp peak in the GC. If you are not giving the split ratio, what will happen? There will be column overload and you will not get separation and you will get broad peak like this. That is the reason a split ratio is kept in GC. Now I am going to discuss GC separation mechanism. Let us assume sample contains butanol, pentanol, hexanol, and we have to separate it on DB5 column, which contains 5% diphenyl and 95% dimethyl polysiloxane. When we will inject the sample in GC, position of all component means butanol, pentanol and hexanol will be at the same place at T0. After some time, what will happen? This is the position of hexanol, this is the position of pentanol, this is the position of butanol. Now you can ask the question why? The reason is that butanol is more polar among all the three compounds, and that is the reason it interacts less with the stationary phase and it tries to come out fast from the column. After some time, what will happen? Butanol will elute, detector detects it and send the signal to the data processor, and data processor convert it into the peak of butanol. After that, pentanol will elute and we will get peak of the pentanol. After that, hexanol will elute and we will get peak of the hexanol. And in this way, we get GC chromatogram of the sample mixture containing butanol, pentanol and hexanol. Modes of calculation. In industry, three modes of calculation are widely used. First is area normalization method or area percent method. Second is external standard method. Third is internal standard method. Area normalization method is generally used to calculate purity and impurity profile. Now question comes how it is calculated. In area normalization method, sample is prepared and injected as per method and chromatogram is generated. Suppose we have to calculate percentage of D, then it will be calculated area response of impurity D divided by total area into 100. Suppose we have to calculate percentage of impurity C, then it will be calculated area response of C divided by total area into 100. Suppose we have to calculate area response or percentage area response of impurity A, then it will be calculated area of impurity A divided by total area into 100. This is the procedure to calculate purity or impurity by area normalization method. In external standard method, both standard is prepared and sample is prepared and injected in GC and chromatogram is generated, and percentage of compound is calculated by this formula: area response of impurity in sample divided by area response of impurity in standard into dilution factor of standard divided by dilution factor of sample into 100 into potency. Internal standard method. In internal standard method, a diluent is prepared containing internal standard having the GC response. Then after, sample and standard is prepared in that internal standard and injected in GC. And we get chromatogram like this. For standard, we get peak area for standard as well as peak area for internal standard. In standard we get peak for the internal standard and peak for the sample, and we calculate impurity or assay by this formula: area response of sample divided by internal standard divided by area response of standard divided by area response of internal standard into dilution factor of the standard divided by dilution factor of sample into 100 into potency. Please keep in mind, weight of standard is not used in the calculation. Secondly, keep in mind, internal standard is used to reduce injection error. Since in GC we are generally injecting 0.1 microliter or 0. Now I am going to discuss GC detectors. The following detectors are widely used in the industries: flame ionization detector or FID detector, GCMS detector or MS detector, thermal conductivity detector or TCD detector, electron capturing detector or ECD detector, nitrogen phosphorus detector or NPD detector. Out of these detectors, FID detector is widely used in the industries. Now question comes, why? I am going to discuss in next slide. This is the FID detector image. I am not going to discuss in detail since I have already discussed in the Now question comes, which type of compound can be analyzed on flame ionization detector? Please keep in mind, only those compounds can be analyzed on FID which has carbon and hydrogen atom. Secondly, which has oxidizable carbon atom. Nitrogen or helium is used as a carrier gas while using FID detector. Response is directly proportional to the concentration of the sample. As I told you, compound must have the oxidizable carbon atom like toluene, benzene, ethanol, methanol, isopropyl alcohol, acetone can easily be analyzed on GC using FID detector. For example, HCl, CO2, formic acid, these compounds having not any oxidizable carbon atom, and therefore these compounds cannot be analyzed in GC using FID detector. Mass detector is used to structure elucidation and for quantification at very low level like quantification of genotoxic impurity. It is costly detector. How to operate GC? Following points must be keep in mind while operating GC. You have to set up the instrument like check the GC system, install the column, carrier gas, detector, system leak test using soft solution. You have to prepare diluent, QL solution, DL solution, SST solution, standard solution and sample solution. Then you have to inject as per method and run the analysis. After that you have to generate the chromatogram, and from the chromatogram you have to calculate assay or impurity profile or related substance or purity as per your requirement. Application: GC is widely used for identification test. It is used for monitoring the reaction. It is used for purity test, it is used for assay test, it is used for content test, carry over test. Nowadays, GC is also widely used for chiral impurity separation. GC having also other application in environmental analysis, in forensic science, and in clinical analysis, in pesticide, etc. For identification test, a standard containing all the impurities or component is injected. Then after sample is injected, then RT of sample of any component or required component is correlated with RT in the standard chromatogram, and then component is identified based on matching of the retention time. Suppose impurity C is matching with the peak 4 in the standard, then impurity C will be 4. Similarly, impurity D is matching with the peak 7, then impurity D will be 7. Suppose impurity E is matching with peak number 53, then impurity E will be 53, like that. GC is also used for quantitative analysis like assay test and content test. Following formula is used for quantification: sample area divided by standard area, standard weight divided by standard dilution, sample dilution divided by sample weight into potency divided by 100 minus water or loss on drying into 100. If we are using internal standard, then this formula will be advantages and disadvantages of GC. In GC we get result fast. GC is a cost effective analysis. GC gives reliable, precise and accurate result with high sensitivity. In GC we get the sharp peak and selective peaks. In GC a small amount of sample is consumed. Secondly, it has advantages also. Non-volatile compounds cannot be analyzed in GC. Thermally unstable compound cannot be analyzed in GC. Now question comes, how to design a new method after the method development. A method must contain chemical and reagents with all details like part number and purity and expiry date, instrument details with detector, column details with part number and manufacturer name, injector temperature, detector temperature, oven temperature, carrier gas, flow rate, injection volume, run time, diluent, sample, standard sensitivity solution and SST solution procedure, retention time and relative retention time in tabular form, system suitability acceptance criteria, procedure of injection and calculation, typical chromatogram of DL, QL, diluent, standard, SST and case study of a new method. Instrument, it must contains like gas chromatograph equipped with flame ionization detector or any other detector as per application. Column like DB5 30 meter into 0.53 mm 1.5 micron, part number so and so or equivalent. Chromatographic condition like initial oven temperature, initial holding time, initial ramp rate, intermediate oven temperature, intermediate hold time, final ramp time, final oven temperature, final hold time, injector temperature, detector temperature, carrier gas flow rate, injection volume, dilute, uh, system suitability solution, preparation of SST, QL, DL, standard solution, procedure of injection and calculation procedure like this, and then typical chromatogram of DL, QL, system suitability, sample solution and standard solution. This is the SST solution with all the detail in the report as required. GC method development steps, it includes selection of the column, try to match stationary phase to sample polarity, like interact, like I have already discussed in the previous slide, column diameter, column length. On increasing the column diameter, resolution is decreased. You have to keep in mind. On increasing column length, resolution is increased. Stationary phase thickness, on increasing stationary phase thickness, column sharpness is decreased. How to improve resolution? I have already discussed here. Secondly, you can reduce the flow rate. You can also improve resolution with the help of temperature programming. Choosing the injection method, a split injection is best for high concentrated samples. I have already discussed. Case studies. How to separate benzene and toluene. Suppose we have to separate sample containing benzene and toluene. See, both are non-polar molecules. Then our stationary phase will be non-polar like dB1 or dB5, dB1 or dB5. Okay, simply use this stationary phase and inject the sample. First peak will be benzene and second peak will be toluene. Keep in mind injection volume, sample preparation, carrier gas, other things you have to optimize. How to separate ethanol and acetic acid. Both ethanol and acetic acid is a polar molecules. Then which column one should select for separation? Definitely polyethylene glycol is the best column or stationary phase for separation of these molecules. What will be elution pattern? First acetic acid peak will elute, then after ethanol peak will elute. This is the acetic acid and this is the ethanol peak. How to separate methanol, ethanol and acetonitrile? These molecules have a different polarity. You can separate easily on intermediate polar column like dB6 to 4. First methanol will elute, then after ethanol will elute, then after acetonitrile will elute in this column. This is the methanol, this is the ethanol, and this peak will be acetonitrile. Overall conclusion is that based on polarity, we have to select the stationary phase of the GC. Know about your coach. My name is Dr. Pramod Kumar Pandey. I am BSc Honours, MSc, PhD in Chemistry, PG Diploma in Patent Law. I am founder of Pharma Guru. I am an analytical research expert with more than 30 years of experience of working in Indian and global pharmaceutical company. I have exposure of several regulatory audits related to US FDA, KFDA, EMA, Health Canada, PMDA and ANVISA. I have practical experience of over 1000 training at various fora, Indian as well as global platform. Now I am on mission to transfer my knowledge with pharma professional through my website PharmaGuru. PharmaGuru's courses. PharmaGuru provide several courses like free online pharmaceutical training programs. This is a free of cost, but little amount of money is taken for registration purpose. Second is most popular online pharmaceutical training program. This is payable and it is completed in 10 to 12 sessions every day 60 to 90 minutes. Advanced online pharmaceutical training programs. This is also payable and this course is completed 12 to 15 days every day 90 minutes to 2 hours time. Best pharma training program for corporate teams. This program has been especially designed for corporate leaders who want to enhance their knowledge in analytical research. Topics to cover mainly with analytical research such as impurity control, strategy, analytical method development using different techniques like chromatography, spectroscopic, titration method, mass spectroscopic method, analytical method validation using different techniques like HPLC, GC, GCMS, LCMS, spectroscopy method and chemical titration method, chiral method development using techniques like HPLC and GC, chiral complexities in APIs, challenges and solution. Here we are providing the solution how chirality issues can be resolved of the compound containing multiple chiral atoms. For example, molecule like sulfosbuvir, edoxabine, etc. Analytical techniques. We provide training on analytical techniques in details on HPLC, GC, TLC, GCMS, etc. Genotoxic impurity, GLP, how to avoid deficiency letters, etc. Each course is explained taking real case studies with a lot of FAQs and interview questions for better clarification. Top interview questions related to GC. These are the questions generally asked in the interview. This is all about this session. Thank you. Let us see you in next session.